Hello, we are Group 24 and our topic is data mining and e-commerce. So, to start off, our project looks at how different data mining techniques, mainly association rule mining, are used across e-commerce. E-commerce platforms generate massive amounts of transactional and behavioral data, and each paper in our presentation uses ARM in a slightly different way. Whether it's profit-focused mining, fuzzy rule extraction, distributed map reduce models, sequential pattern mining, or applied cases like product purchases and website navigation. Overall, all of these approaches try to uncover hidden patterns that help improve recommendations, marketing decisions, and the overall customer experience. The first paper I looked at focuses on customer purchase behavior. It uses a real UK online retail dataset, and the idea is to find which products tend to be purchased together. The author applies the classic ARM algorithms a priori, FP growth, and ECLAT, and the goal is pretty straightforward. Discover buying patterns that can support bundling, promotions, and recommendation systems. So this slide shows the pipeline that the authors used, and I'll just walk through it quickly. First, the transaction data is cleaned and converted into a proper format for rule mining. Then they run the three ARM algorithms to find frequent item sets, and from there they generate association rules. The strong rules are selected using support, confidence, and lift, which helps filter out patterns that aren't meaningful. What's interesting is that they actually validate these rules using decision tree and random forest models. That part helps check whether the patterns genuinely help predict customer behavior. From the results, FP growth performed the best. It was faster and produced high quality item sets. The high lift rule clearly shows strong cross product relationships, the kind of insights companies use for cross selling. And when these rule based features were tested in predictive models, random forest gave the highest accuracy. So overall, the patterns they found matched real customer behavior pretty well. The second paper I looked at shifts from product purchases to how users navigate across an e-commerce website. So instead of transaction data, this one analyzes clickstream logs, basically the sequence of pages a user visits. The idea is to uncover browsing patterns that can help improve the structure and usability of the site. Here again, they use a priori to find frequent page sequences. This diagram on the slide breaks down the full workflow. They start by pre-processing the raw web logs, removing noise and grouping everything into user sessions. Each session is then turned into a sequence of page visits, and then a priori is run on those sequences to generate navigation rules. An example of this is a rule like home plus search tends to lead to a product page. These rules basically highlight the common and reliable user paths through the website. The results reveal the most frequent navigation journeys, including the ones that consistently led to checkout, and also the paths where users tend to drop off. These insights are useful because they help identify what parts of the site are working well and where users might be getting stuck. Overall, this paper shows how association rule mining can help improve website usability just by analyzing real clickstream behavior.
So the first article I chose introduces a new way to mine association rules that focuses on profit rather than just frequency. This article is titled An Association Rule Algorithm for Online E-commerce Recommendation Service by Dai and Zhang. So the main issue the authors identify is that traditional algorithms like a priori use one single minimum support value for every item. In e-commerce, this is a problem because many items can be rare but highly profitable, while common items can generate very little profit. So a single min support can remove those rare profitable items even though they might matter most for business. As a result, association rules get dominated by cheap, frequently bought items, and the model misses the items that actually drive revenue. To approach this problem, the authors use a synthetic e-commerce dataset generated with IBM's transaction generator, including 1,000 items and 10,000 transactions, with an average of 10 items per transaction. Each item in the dataset is assigned a profit level, low, medium, or high, to simulate real-world e-commerce products. So this setup allows the authors to test whether the profit-based minimum support actually improves the quality of discovered rules. So to address the previously mentioned problem, the authors propose an algorithm called PARMA, the Profit Support Association Rule Mining Algorithm. PARMA assigns a different minimum support value to each item based on its profit. Firstly, all items that fall under the minimum total profit threshold are removed. In this table, we can see that items 3 and 4 are removed since they fall under 100. So after filtering out those low profit items, the authors show in the image below how they set the unique minimum profit support, as we can see here. So the table to the right shows how the authors evaluated the performance of the proposed algorithm by comparing it to amount-based association rule mining with multiple minimum support, also known as MMS a priori. While MMS a priori makes quantities of items as the optimization goal, the PARMA approach considers the profit of each item. However, it is worth noting that both algorithms follow a similar structure, and the only difference is of item sets of size 1. So after that, both algorithms generate larger item sets in the same way. The authors found that PARMA produces fewer large item sets, meaning the rules are more focused and less noisy. PARMA also generates more high-quality rules because rare high-profit items aren't being filtered out. PARMA generates more candidate item sets overall, meaning it explores more potential profitable combinations. The authors argue that this is what makes PARMA more efficient, since it directs its search toward high-value item sets rather than simply frequent ones. So in terms of limitations, the first major one is choosing the right minimum total profit threshold, since this greatly affects the results. PARMA is also more computationally expensive and requires accurate profit data, which can change very quickly in real e-commerce environments. The authors suggest future work on improving parameter tuning and reducing runtime. So the second paper I chose is titled Efficient Discovery of Association Rules in E-commerce, Comparing Candidate Generation and Pattern Growth Techniques by Hunyadi, Constantinescu, and others. This article compares two major association rule mining algorithms, a priori and FP growth. These algorithms are widely used in e-commerce to find purchasing patterns. So the goal of this study was to evaluate how a priori and FP growth differ in speed, memory usage, number, and strength of rules they generate, especially under different support thresholds. To compare a priori and FP growth fairly, the authors used a real e-commerce dataset and applied the same pre-processing steps to clean it and reduce unnecessary complexity. They then built two workflows in RapidMiner, one for a priori and one for FP growth. Both use the same parameters and the same dataset to make the comparison fair. They changed minimum support from 0.1 to 0.15 to 0.20 and confidence from 0.1 to 1 in increments of 0.05 to see how algorithms perform under different workloads. The results from RapidMiner were then exported and subjected to statistical analysis using IBM's SPSS statistical software. So things like descriptive statistics, normality checks, one-way ANOVA, Kruskal-Wallis test, and Pearson correlation were used to validate performance differences and assess relationships between algorithm outputs. Now for the results. They compared speed, memory usage, number of rules, quality of rules, and how results change when support and confidence were raised. They found that FP growth execution times were normally distributed, while a priori was not normal at some support levels. ANOVA on FP growth, which was used since distribution was normal, showed that the support level significantly affects FP growth's time. Kruskal-Wallis on a priori, which was used because a priori data was not normal, found that a priori is very sensitive to support changes. Finally, Pearson correlation found a strong linear relationship between the rule counts, suggesting that the output of one algorithm can serve as a reliable predictor of the other under similar parameter configurations. So the top graph here shows the support versus mean of association rules generated by both algorithms. As we can see, FP growth generates many more rules than a priori, even at the lowest support. The bottom graph shows the memory usage at different support thresholds. So the main pattern here is that FP growth consistently uses less memory than a priori across all support levels. So overall, FP growth is faster, uses less memory, scales better, produces more rules, especially at lower support levels, while a priori is slower, generates fewer rules, and becomes inefficient when support is low. Through linking their results to e-commerce needs, they state that FP growth is better for large datasets and real-time recommendation systems, while a priori may still be preferable if someone wants more interpretable steps, like for teaching or smaller datasets.
My name is Marc, and my first paper is MapReduce framework-based sequential association rule mining with deep learning. The problem highlighted in this paper is that traditional R methods suffer from high computation time, inefficient use of resources, and that sequential rules and user category predictions are difficult at scale. To address this, the authors developed a hybrid approach by combining an optimization algorithm called TWDO-SAM together with the MapReduce framework and deep learning classification. So MapReduce is used here to split the mining task across multiple nodes so the process becomes much faster and more scalable. The mapper's job is to take chunks of the dataset and to generate candidate 2 and 3 item sets. It then applies the optimization filter to select the most promising rule candidates. It then, once it's sent to the reducer evaluates the rules using thresholds for minimum support and confidence. And once the final rules are generated, a DCNN or deep convolutional neural network is used to classify customers based on their purchase behavior which can then be used for personalized marketing. So they tested this using the one dataset, and compared to all the other algorithms, you can see that they mined 183 rules, which is the highest amongst all the other algorithms. It also reduced the execution time to 7.7 seconds, making it the fastest. And it achieved strong predictive performance with recall at 0.88 and precision at 0.87. This shows that the method is both efficient and effective for large-scale retail mining. In terms of advantages, the approach offers very strong scalability, improved rule quality, and noticeably better execution time compared to existing methods. However, there are some limitations. The transformation of rules into DCNN input can lead to some information loss. The entire process is still a little bit computationally heavy due to the optimization filter. And since they only use one data set for testing, the generalizability of the model beyond like retail data sets is still unclear. As for my second paper, integrating fuzzy set theory with ARM for advanced recommendations, this paper addresses a different challenge. Traditional ARM ignores things like price, quantity, and vague consumer behavior, and produces trivial rules that are not meaningful for recommendations. So the authors propose integrating fuzzy set theory with ARM to capture more human-like and context-aware patterns. First, fuzzification is performed, where attributes like price and quantity, as you can see in this example, are converted into fuzzy categories such as cheap, medium, or expensive, with membership values like 0.7, 0.3, and 0 for quantity. Secondly, the fuzzy transactions are then processed using the a priori algorithm to generate fuzzy frequent item sets. Finally, the rules are then evaluated using a comprehensive set of statistical validation metrics. So as they tested this using three different data sets, and the results show that fuzzy ARM generates much more context-aware and meaningful rules. For example, patterns like low quantity and cheap items often show very strong associations. Many rules achieve lift values greater than 10, and some rules showed extremely high chi-square values with p-values close to 0, which indicates statistically strong relationships. In terms of advantages, this approach handles uncertainty and produces more realistic recommendation insights and performs well across multiple datasets. However, fuzzification does increase computational costs, and it does require domain knowledge to define the membership functions. And it's still not optimized for real-time, large-scale environments like MapReduce.
Hi, my name is Ahmed Elag, and the first paper I looked at is E-commerce Recommendation System Using Association Rule Mining and Clustering by Vishal Parikh and Parth Shah from Nirma University. It focuses on big e-commerce sites with huge product catalogs where customers can easily get overwhelmed and miss products they would actually want. Their goal is to build a recommender system that turns raw transactions, like clicking customer products and purchases, into more personalized suggestions. But as the transaction data grows, running association rule mining on all of it becomes too slow for real-time recommendations. So, method-wise, everything is built on association rules of the form A implies B. Support tells us how often A and B appear together, and confidence tells us how often B appears when A appears. They use three main modes. One, profile-based recommendations that use age, gender, and location. Two, social friend recommendations based on what your friends buy. And three, cart-based recommendations that look at items already in the basket and suggest common add-ons. All three modes mine rules from the same large transaction database. So as the data grows, plain ARM becomes computationally expensive and too slow for instant recommendations. So to tackle the speed issue, the authors add hierarchical clustering instead of mining rules on the whole dataset. They first cluster the transaction by gender, then by age group, then by location, and finally by products, keeping each final cluster below a certain number of transactions. Then, they run association rule mining inside each cluster instead of all the data all at once. That way, each mining job is smaller and more focused on a particular group of users or products. In their experiment with 10,000 transactions, the timing charts show recommendation times dropping as shown in the diagram. So, they trade some extra pre-processing for much faster recommendations, which makes an ARM-based recommender actually usable in near real time. The second paper I chose is Association Rule Mining Algorithm Implementation for E-commerce in the Retail Sector. Here, the goal is to analyze real customer buying patterns in the retail sector to improve revenue, service quality, and customer satisfaction. They use invoice data from 2020, about 580,000 transactions, and 242 different products from a department store in Bishkek. The data covers 8 municipalities and 9 cities. Bishkek alone makes up about 64% of all sales, while places like Bakken are only around 1%, which shows a big gap between the capital and other regions. On top of this, they apply a priori algorithm for market basket analysis. So, in terms of methods, they load and clean the data with Python and Pandas and then look at which products sell the most. Tropical fruit is a top selling product. The top 20 products make up about 62% of all sales, and the top 5 make about 26%. To keep things manageable, they focus on popular items and work with about 360,000 invoices instead of the whole data set. They then run a priori with minimum support set to 40% and minimum confidence set to 80%, and they end up with 118 strong association rules. One example is tropical fruit 100 grams implying kids biscuit 100 grams with about 61% support and 79% confidence. These rules highlight which products are often bought together and can be used for cross selling, promotions, product placement, and better recommendations. So, if we compare the two papers, both use association rule mining in the e commerce setting, and both try to turn raw transactions into patterns that help with decisions. The first paper focuses more on the system design and performance side of things, and show that combining association rules with hierarchical clustering makes recommendation times fast enough for real time or near real time use. The second paper, on the other hand, focuses on large, real world retail data and shows how a priori can pull out 118 strong association rules that directly support marketing and inventory planning. Both mainly rely on classic support and confidence. A natural next step would be to add things like profit, time, or even fuzzy categories, and to use distributed or incremental mining so these systems scale to even bigger datasets and stay closely tied to business goals. So, to sum up the big picture, across all of this work, association rule mining is very flexible for e commerce and it can be used to study products, customer behaviors, pricing, and even how users move throughout a site. Different versions of ARM handle different kinds of challenges: traditional a priori and FP growth for transaction data, Parmo when we care about profit, fuzzy ARM when there's a little bit of uncertainty, and MapReduce style ARM when we need to work with very large distributed datasets. But the common goal is always the same: find meaningful, high value patterns that help with decisions in retail, marketing, and user experience. The key outcomes are better recommendations, better usability, stronger targeting of customers, and more efficient processing of large datasets. In that sense, ARM gives us a nice closing loop to the course. It shows how everything we've talked about ultimately comes down to seeing structure in data and turning it into decisions that actually matter. Thank you very much for your time, and thank you for watching.